When a data center's primary cooling plant fails, the facility has seconds to adapt before the servers overheat. This total loss of primary chillers forces the system to rely entirely on stored thermal energy to survive. To guarantee survival, engineers establish a strict physical line known as the protected thermal service boundary. This isolates the critical cooling load from the failed primary plant. This diagram shows the spatial relationship across that boundary. On the exterior, you have the primary production side, the air-cooled chillers. Inside the boundary, you find the critical delivery side, which includes the central stratified tank and the data hall CRAH units. Sizing this protection requires exact baseline inputs. Engineers must define the concurrent critical load, say 5.0 megawatts, the required ride-through window, such as 30 minutes, and the usable temperature difference, or delta T, of the water. This establishes the proven path rule, claiming you have stored energy, unless the water path, the control state, and the failure response are physically verified in the field. Moving from the blueprint to the actual hardware skid, we can trace the complete thermal storage service path. The sequence begins at the charge pumps, moves through the insulated thermal energy storage tank, and arrives at the plate heat exchanger. The charge and discharge pumps push the water through this sequence. Because system resistance changes constantly, these pumps rely on variable speed drives and check valve isolation to maintain precise control over the flow. The plate heat exchangers and decouplers serve as the physical gatekeepers of the system. They enforce fluid separation and pressure boundaries between the primary plant and the critical load. Real-time performance evidence is captured by critical accessories along the pipework. 4-corner resistance temperature detectors, flow meters, and differential pressure sensors constantly feed data back to the controllers. For a data center to achieve a Tier 3 or Tier 4 resilience rating, this specific hardware lineup must successfully operate across normal conditions, routine maintenance, and single failure states. Inside the thermal energy storage tank, the entire system relies on fluid density stratification. Warm water floats, and cold water is denser. During a discharge cycle, buoyancy-driven flow allows the densest, coldest water to reliably exit from the bottom. Looking closely at this cross-section, the storage volume is divided into distinct zones. Notice the top and bottom deadbands, which represent volume lost to diffuser clearance, and the central thermocline, the transitional layer of mixed water. Because of these physical realities, the gross volume of the tank never equals the usable volume. The space taken up by the diffusers and the thickness of that thermocline restrict exactly how much cold water is available to the servers. To preserve these layers, engineers restrict the water velocity at the diffusers to strictly under 0.15 meters per second. This low velocity ensures buoyancy forces dominate over momentum. If the velocity exceeds that limit, jet impingement occurs. The fast-moving water destroys the stratification, violently mixing the hot and cold layers and instantly ruining the tank's cooling capacity. To prevent a shortfall, the required volume is calculated using this formula, which factors in the critical power load and required hold time. Notice the variable at the end, the usable factor, which mathematically corrects for that lost volume. In operation, the system determines its exact state of charge by integrating data from a vertical array of temperature sensors mounted along the height of the tank. A credible state of charge calculation depends on the entire validated vertical profile. The control logic is programmed to reject impossible temperature gradients or single sensor jumps that could falsely report readiness. This matrix outlines the 4 primary hydraulic strategies: stratified storage, buffer vessels, plate heat exchanger separated loops, and decoupling. The design gate dictates which arrangement matches a facility's specific failure criteria. Plate heat exchanger separated loops establish a hard physical wall in the system. This provides a strict pressure boundary that completely isolates the potentially dirty exterior primary loops from the pristine secondary loops serving the data hall. For systems using primary-secondary decoupling, stability relies on a shared section of plumbing known as the common pipe. This connects independent pump circuits without forcing fluid across a physical plate. Decoupler flow is calculated by subtracting secondary flow from primary flow. The resulting sign indicates the direction of the water, which flips depending on whether the chiller plant is overproducing or underproducing relative to the data center's demand. How a system responds to that demand depends on its tier architecture. A Tier 3 system uses shared headers and a frozen demand logic to manage the transition, while a Tier 4 system uses completely segregated trains that calculate residual chiller capability locally. Regardless of the tier, the decoupler's flow direction acts as the ultimate physical proof of the plant's production state versus the actual IT load. This diagram maps the operating state machine through its cycle of standby, charge, discharge, and recovery. Notice the abnormal path at the center, which becomes the immediate priority during a chiller trip. Looking at the exact chronological sequence of a loss of chiller event, the ride-through timeline begins precisely at T0, when the system detects the failure and bounds any false trips. Within the first 2 seconds, the system enters the freeze stage. It explicitly blocks any charging commands and latches the valves in place to prevent hydraulic disruption. By second 5, it begins opening the discharge path, and by second 10, the pumps start. That open path stage is non-negotiable. The controller must physically prove the valves are in the correct open positions before it ever sends a start command to the discharge pumps. By the 20-second mark, the stabilization window closes. The header supply temperature and the differential pressure must be firmly back inside the safe operating envelope. The system then enters the hold phase. The controller continuously tracks the state of charge and calculates the remaining minutes of cooling, guiding operators if they need to escalate to backup sources. A commanded transition means nothing if the water doesn't stay cold. A ride-through is only successful if the thermal result is proven under a live load. Validating this sequence requires 5 distinct levels of commissioning. This staircase culminates at the final acceptance gate, where the transition, field state, and recovery are proven together. Component tests are insufficient. Level 5 integrated system testing is the only phase that verifies the complete chain of evidence, from the initial trigger all the way through to thermal stabilization. When a test fails, engineers execute a failure mode and effects analysis to troubleshoot from the thermal symptom back to the physical cause. Steps 3 and 4 are critical here, verifying the thermal energy data and then verifying the hydraulic flow and pressure. For example, if the header supply temperature is uncertain or the water path is unverified, the operator must immediately stop and execute the abnormal path fallback sequence to protect the load. Troubleshooting often reveals that architectural redundancy is an illusion if parallel equipment shares a single sensor array or controller. These single points of failure act as common mode hold points that can bring down the entire plant. Once primary power is restored, the facility enters the recovery state. The system must transition from the stored energy back to the primary chillers smoothly, without inducing a hydraulic shock. During this phase, the critical IT load is always served first. The storage tank is strictly recharged using only the verified residual cooling capacity left over from the primary plant. This requires a bumpless return logic. The controller ramps the thermal storage duty down to 0 while continuously verifying the new chiller supply temperature is stable. The system only returns to the ready state when the tank reaches full capacity, all alarms are reset, and automatic control authority is successfully reproven. Ultimately, a survival event is not finished when the chillers turn back on. It is only over when the complete evidence chain is indexed and the system is safely restored to a physically proven ready state.